Hello, my name is Todd Rothman. Welcome back to Organic Chemistry 1. In this video, we're going to learn about how forces allow molecules to come close together to interact with each other. Okay, so the different forces that keep molecules together. And what we're going to see is we have three topics to cover. The first thing is states of matter, just a quick review on what that is. We'll talk about the difference between intramolecular and intermolecular forces. And then we'll follow up by just discussing more details about each force. All right, let's get started. So the first thing is, what are the states of matter that we need to know? And here they are. There's three. We need to know the solid, the liquid, and the gas phase. So these are the different states of matter. Now, the idea here is that obviously, if you use heat or pressure or both, you can actually convert from one state to the other. But what actually makes a solid? Well, here are the just three bullet points that I wanted to put out. The first thing is that they don't really move around. They have vibration. They vibrate, but they don't move. So these molecules are packed together tightly. And they have a very specific order of arrangement. So they have a specific form, a specific shape. They don't occupy the volume of the container that they're in. And like I said, they have a definite shape and volume. Now, unlike solid, when you look at a liquid, they do move. They slide past each other, so they have motion. They are still close together, just like in a solid, but there's no regular arrangement. And it does take up the shape of the container. So it has a definite volume, but not shape. Okay? So solid has shape, whereas in the case of liquid, it has a definite volume. Solid has shape and volume. Liquid has volume, but not shape. And then finally, if you continue to apply energy, then you could separate them even further, and that'll give them no regular arrangement, and it will take up both the shape and the volume of its container. Okay, so these are the different states of matter, and all I want to do is review that with you here. So now let's talk about the next thing, which is intramolecular versus inter. Now we're going to hear about this all semester long, inter and intra. Now intra is within yourself, within itself. So intramolecular force is a force that occurs within the molecule. And there are three types that we already know. These are basically the bonds that allow molecules to become molecules, right? These are how atoms come together to make molecules. And that's ionic, covalent, and polar covalent bonds. So those are the types of intramolecular forces. And then there's inter. Now, inter is, you're going to hear this again over a few different ways. There's intra and inter. Inter is where things that are outside of the molecule. So it's forces outside the molecule. And it's either attractive or repulsive forces. And it's between molecules, not within one molecule. Okay. And by the way, molecule, atoms, or even ions have this. Now here are the different types. There's the ion dipole, the dipole-dipole, hydrogen bonding, and London forces. Now, I did make a note here about van der Waals. Let me just emphasize something, because even my note is wrong from your book. So let me make this clear. Van der Waals is really the sum of all forces that are nonpolar. So van der Waals is the sum of all non-charge forces. Okay, so what I mean is it would not ions, but things like dipoles or van der Waals would be like a London dispersion, and even in some textbooks, hydrogen bonding, because there is not a charge there. But again, it depends on your source. So I wrote that van der Waals only includes dipole, and it also includes London dispersion, but I didn't say it includes hydrogen bonding. But then I looked at your book, and your book says it does include hydrogen bonding. So, if you do a Google, like for example, go to Wikipedia and look up London forces, you'll see that it excludes hydrogen bonding, but your textbook includes hydrogen bonding. So, just keep that in mind as far as what van der Waals forces means. It really depends on the source that you're looking at. All right, but in general, it definitely means all non-bonding interactions and that are not with charges. Okay, so full charges, partial charge, no problem. That's like dipole, for example. Anyway, so here's the trend. The trend is, in terms of increasing force, ion is the strongest. So that one would require the most amount of energy to separate. That's an intramolecular force. So is covalent. But ion is stronger than covalent. If you need to separate a covalent bond, break apart the bond, then it requires less energy than if you try to separate two ions that are positive and negative from each other. Okay? Now, the rest of them are intermolecular forces, and so ion dipoles at the top. We'll see what that is in the next page. Hydrogen bonding next. Keep that in mind. This is a very important trend, especially the bottom four, dipole, and then London is the weakest force. Now, that means it requires the least amount of energy to separate the molecules from each other. Okay, now let's just finish up this video by looking at each individual force. So an ion, like I said, is where you have two opposite charges, full charges, plus and minus, and they are drawn together, right? That's the ionic bond that we talked about. Now, an ionic bond is a very powerful intramolecular force, and of course it's between a metal and a nonmetal, and that would require the most energy to separate. That's why it's at the top of our list. Covalent bond is next. We've already talked about this. This is also an intramolecular force, and so nothing really new to say about that. Now, as far as the intermolecular forces, let's review that now. Well, this is the first one, and this is at the top of our list of intermolecular forces. This is the strongest intermolecular force, and that's known as an ion dipole. Now, we all know that a dipole exists, and we talked about this in Chapter 1, where you have atoms with different electronegativities. So, for example, if I have a carbon bonded to fluorine, we know there's a dipole. This is partial negative, partial positive. This is partial negative. The electrons are moving towards fluorine. Now, since the electrons move towards fluorine, that means that if you have a positive source, it'll be drawn over to the fluorine. And there's a force, an attraction between here, that yellow here, and that is the intermolecular force that we're referring to. This is an ion dipole. Okay? And I'm showing you water up here as an example. So if something is positive, it'll go towards the oxygen. Remember, oxygen is more negative and the H's are more positive. If something is negative, like Cl minus, it'll go towards the H's. And so there'll be some sort of interaction, some sort of attraction. That's what the dotted lines are, and that's what draws them together. Okay, so this is the ion dipole. Now let's talk about the next one up on that list, and that's hydrogen bonding. Now with hydrogen bonding, we have to have one of these three atoms in order to have hydrogen bonding, either an O, an N, or an F. Now, those are required to be in the molecule for hydrogen bonding, but not just NOF, they have to be bound directly to an H. So OH, NH, or FH. Those are the ones that do hydrogen bonding. Now, hydrogen bonding is a special characteristic because it is a dipole force because it's polarity. Think about it. Oxygen is more electronegative than H. Same with fluorine, same with nitrogen. So there's a dipole, but this is a special type. It's stronger than any other dipole, which is why we have its own category. So here's an example of it where there's an H from this alcohol attracted to the O of water, while water's H is attracted to the O of the alcohol. So that shows a hydrogen bonding that's taking place between the solution, water, and the alcohol next to it, that's inside the solution. Okay, so that's an example of it. Now, what I want to point out is a little bit somewhat interesting, is that if you look at the electronegativity values, oxygen is a 3.5, nitrogen 3, and fluorine is 4. Those are the three highest numbers from our electronegativities. So they're the most electronegative. And that's why they have hydrogen bonding, as long as there's an H on those atoms. But a common question is, if we look over here on this right here, this electronegativity table, look at chlorine. Chlorine is more electronegative than nitrogen. So if nitrogen has hydrogen bonding, why doesn't chlorine have hydrogen bonding with an H on it? And so that's the interesting